Hello everyone. In this video, I will be explaining series solution of Bessel's differential equation which leads to Bessel function. If you are watching my video first time or if you have not subscribed my channel yet, subscribe this channel and also press the bell button to get more updates of videos which I am going to upload here. Similarly, if you like this video, give like button in the YouTube channel. Now, I'll explain what is Bessel's differential equation is. So we have Bessel's differential equation is x square d square y by dx square plus x dy by dx plus x square minus n square of y equal to 0. This type of special differential equation, we call it as Bessel's differential equation. Now we will solve this differential equation by series solution method. For that, let us assume the solution for this differential equation as y. So assume y equal to summation r from 0 to infinity ar x power k plus r. Here y expression, this summation is an infinite series, so we are following the series solution method. And let me consider this solution as equation number 2 and given differential equation as equation number 1. Now, in this differential equation, we have d square y by dx square term as well as dy by dx term, similarly y term. So we have to replace for these terms. Of course, we have y equal to expression, that is equation number 2 we can replace here. Now we need dy by dx as well as d square y by dx square. So let us find it. So dy by dx can be found like this. Just differentiate y, that is summation r from 0 to infinity ar x power k plus r, we have to differentiate to get dy by dx. Here derivative of x power k plus r will be k plus r into x power k plus r minus 1. This is what our dy by dx. Now to find d square y by dx square, we have to differentiate dy by dx once again. So we get summation r from 0 to infinity ar k plus r k plus r minus 1 into x power k plus r minus 2. Now these terms we will substitute in equation number 1. That means in the place of d square y by dx square, we will replace this expression. In the place of dy by dx, we will replace this expression. In the place of y, we will replace this equation number 2. See what happens. So just simply replaced these altered expressions. Now let us simplify. Here x square we have outside to the summation and x power k plus r minus 2. We will club this x power so that in next step we can write x power k plus r. Here x is there in outside to the summation. X power k plus r minus 1 we have inside. If you club, we will get x power k plus r only. This bracket let us split x square into summations r from 0 to infinity ar x power k plus r, which we can get it as x power k plus r plus 2 minus n square into summation. So there is no change in the summation. So let us do that step. So we get this expression. Now let us club similar terms together. So first summation we have x power k plus r. Second summation we have x power k plus r. And last summation we have x power k plus r. We can club these three terms. And third summation we have x power k plus r plus 2. This third summation we will write first and remaining summation we will write next, and we will do some simplification. That is summation r from 0 to infinity ar x power k plus r plus 2 plus summation r from 0 to infinity. Here ar k plus x power k plus r taken outside, and inside we wrote a k plus r into k plus r minus 1 plus k plus r minus n square. This k plus r plus into k plus r minus 1, we got it from first summation, and this k plus r we got it from second summation. This minus n square we got it from last summation, and written like this equal to 0. Now let us simplify this bracket, that is k plus r into k plus r minus 1 plus k plus r minus n square. If you look it properly, k plus r into k plus r minus 1 plus k plus r, these terms, left side to the plus sign we have k plus r, and right side to this plus sign we have k plus r. We can take outside and we can simplify that. Let me show in the next step. Are taken outside here, so remaining k plus r minus 1 plus 1, this plus 1 from here, because if you take k plus r outside, here only remaining 1. Here k plus in left side we have k plus r minus 1, right side 1, this along with plus sign. So we can write k plus r into k plus r minus 1 plus 1 minus n square, so that minus 1 plus 1 will be 0. So k plus r into k plus r remains minus n square, which means k plus r whole square minus n square. So let us substitute this simplified step in the summation form. So we get summation r from 0 to infinity, ar x power k plus r plus 2, there is no change, plus sigma r from 0 to infinity, k plus r whole square minus n square, ar x power k plus r equal to 0. So let me consider the same step again. Now comparing the coefficient of x power k on both sides. Here least power of x is x power k, because if you put r equal to 0, in the first summation, we get a0 x power k plus 2. So least power of x is here k plus 2. In second summation, if you put r equal to 0, least power of x is x power k. So least power we consider as x power k, and we equate the coefficients on both sides. Right side there is no term, means coefficient is 0. As I already told, in the first summation, it starts from x power k plus 2. So no chance to have any x power k term. So put r equal to 0 and equate the coefficients. We get k plus 0 whole square, because to get x power k we have to put r equal to 0. So x plus 0, k plus 0 whole square minus n square into a0, because r is 0, into a0 equal to 0. Simplify, k square minus n square of a0 is 0. Now setting a0 not equal to 0, because whenever a product of two terms is to be 0, means either first expression should be 0 or second expression should be 0. Here we are setting a0 is not equal to 0. That means surely a k square minus n square should be 0, which means k square equal to n square, or k equal to plus or minus n. So these results are important. So we have to use in the next upcoming steps. Now comparing coefficient of next least power of x. So next least power means putting r equal to 1. Obviously here it starts from, in the first summation, it starts from x power k plus 2 when you put r equal to 0. So there is no chance to have x power k plus 1 term. In the second summation, if you put r equal to 1, we get x power k plus 1. So putting r equal to 1, we get k plus 1 whole square minus n square of a1 equal to 0. This term we get from second summation, putting r equal to 1. So now product of two terms should be whenever product of two terms is 0 means either first term should be 0 or second term should be 0. If I consider first term as 0, that is k plus 1 whole square minus n square is 0, we get k plus 1 whole square is equal to n square, which means k plus 1 is equal to plus or minus n, which is not possible because we already considered and concluded k is equal to plus or minus n. At the same time, k is plus or minus n and k plus 1 is plus or minus n is not at all possible. Therefore, we have to change our selection. That means k plus 1 whole square minus n square is 0. Whatever we have chosen, that is wrong. We have to choose a1 equal to 0. Then only product of two terms 0 means one term should be 0. Then only this result holds. Therefore, we have to conclude that a1 equal to 0. Now, comparing the coefficient of x power k plus r, that is a general term, both sides. First summation, we will get x power k plus r when we substitute r equal to r minus 2. So if you substitute r equal to r minus 2, r minus 2 plus 2 will be r. This means k plus r. So it is possible because we can substitute any value for r from 0 to infinity. So if you substitute r equal to r minus 2 also, it is possible here. So then only we will get x power k plus r. In second summation, no need to replace r equal r by any. So it is just enough to r as keep as enough to keep r as r only. So we get x power k plus r. So left first summation we will get coefficient of x power k plus r as a r plus 2, plus second summation we will get k plus r whole square minus n square into ar, which is equal to 0 because right side there is no terms and it is 0. We will get ar minus 2. It is not ar plus 2. We will get ar minus 2 as we substitute r equal to r minus 2. And this is in the first summation. In second summation we get k plus r whole square minus n square into ar equal to 0. Now let us simplify this. So ar minus 2 plus k plus r whole square minus n square ar equal to 0. Consider the same. Now k plus r whole square minus n square into ar equal to minus ar minus 2. That is ar minus 2 taken right. And now writing an expression for ar which gives minus ar minus 2 by k plus r whole square minus n square, where r is greater than or equal to 2. Because what happens if you put r equal to 1 or 0, here a minus 1 and a minus 2, these does not exist. Therefore it is meaningless if you put r equal to 0 or 1. Therefore r must be greater than or equal to 2. So we get ar equal to this expression. Now we already concluded k equal to plus or minus n. Now if you take k equal to plus n in equation 3, this will reduce to ar equal to minus ar minus 2 n plus r whole square, because k replaced by n, minus n square. Here n plus r whole square is of the form a plus b whole square. If you simplify by opening the bracket, here n square get cancelled with n square, remaining ar equal to minus a r minus 2 by 2nr plus r square. This is what ar. This is very important and we will be using in upcoming steps. Now putting r equal to 2, 3, 4, etc. because r is greater than or equal to 2. So select r values like 2, 3, 4. So we see what happens. R equal to 2 means A2 equal to minus A0 because AR minus 2, 2 minus 2 will be 0 by 2NR. 2 into N into R means 2. So 4N plus R square, which 2 square is 4, which can be written minus A0 by 4 of N plus 1. Now put R equal to 3. We get A3 equal to minus AR minus 2. 3 minus 2 is 1 divided by 2NR. 2NR is 3. So 6N plus R square, this is 3 square is 9 equal to 0. And this equal to 0 because we already concluded A1 is 0. Since A1 is 0, this full A3 is 0. Similarly, A5, if you wanted to find A5, so R equal to 5. So in numerator we have A minus A5 minus 2, that is minus A3 by something. So A3 is 0, therefore this full expression will be 0, which means A5 will be 0. Similarly, if you wanted to find A7, A7 equal to minus A7 minus 2, that is in numerator we have minus A5. Just now we concluded A7 is A5 is 0, therefore A7 will be 0. Likewise, all A3, A5, A7, all odd terms, that is, will be equal to 0. Now we will put R equal to 4. We get A4 equal to minus A2 by 8n plus 16 because 2nr plus nr square, which is 16, which means we write minus 1 by 8 of n plus 2, taken 8 outside, and A2 is there. For A2 we already found an expression like minus A0 by 4 of n plus 1. Simplify. A4 we get it as A0 by 32 into n plus 1, n plus 2, and so on. It continues so on. We just evaluated up to A4. Now, substituting so obtained expressions in expanded form of 2. 2 means our solution y equal to. So our equation number 2 is y equal to sigma r from 0 to infinity ar x power k plus r. If you give r equal to 0, 1, 2, 3, its expanded form will be a0 x power k plus a1 x power k plus 1 plus a2 x power k plus 2 plus a3 x power k plus 3 plus a4 x power k plus 4, just given values for r. Now we just evaluated expressions for a2, a3, a4, etc. If you substitute here, we get, before that we can take x power k outside from the this summation, because in first expression we have x power k, second also we have x power k, third also we have x power k, everywhere we have x power k common. If you take outside, we get x power k into a0 plus a1x plus a2x square plus a3x cube plus a4x power 4, etc. Now we replace for a2, a3, a4, whatever we just evaluated. Putting k equal to plus n, because throughout in the previous steps we have considered k equal to plus n, and so we take k equal to plus n. Also, when we put k equal to plus n, its solution we denote it as y1, because we have another option k equal to minus n, so that solution will take y2. So the solution, let it as y1. So y1 equal to x power n, because k is taken n, a0 plus a1x, a1 is 0, so plus 0, plus a2x square, a2 is minus a0 by 4 into n plus 1x square, plus a3 0, plus a4, a4 is a0 by 32 into n plus 1 into n plus 2 x power 4 plus etc. Now everywhere a0 is common, take outside, and 4 we have written as 2 square and 32 written as 2 power 5. Keep it as equation number 4. So this is when we get when we substitute k equal to n. Similarly, when k equal to minus n, we will get similar solution. So to get that solution, it is just enough to put k equal to minus n in y1 expression. So we get y2 equal to a0 x power minus n 1 minus 1 by 2 square minus n plus 1, because n is k is replaced by minus n, where we see n we replace it by minus n plus 1 x square plus 1 by 2 power 5 minus n plus 1 into minus n plus 2 x power 4 minus etc. This we consider as equation number 5. So complete solution of Bessel's differential equation is given by y equal to a y1 plus b y2, where a and b are arbitrary constants. Y1 and y2 we have in equation number 4 and equation number 5. Let us standardize the solution by choosing a0 equal to 1 by 2 power n of gamma of n plus 1, and that solution, let me denote it as capital Y1. So we have y1 equal to this, we just derived in the previous slide. Now here we have to replace a0 equal to 1 by 2 power n gamma n plus 1. So replaced, same, and inside the bracket we write 1 minus x square by 2 square, let me write x by 2 whole square, and x power 4 by 2 power 5, we just take x by 2 whole power 4, and 1 2 is remaining because total 2 power 5 in the denominator, so 2 power 4 is here to x by 2 power 4, that remaining 2 let me write here as multiplied 2. Now x by 2 whole power n keeping outside to the bracket, and 1 by gamma n plus 1 multiplied inside the bracket. Now we use the property of gamma function, that is gamma of n plus 1 equal to n gamma n, or n plus 1 into gamma n plus 1 can be written gamma n plus 2, or n plus 2 into gamma n plus 2 written gamma n plus 3. This will use in summation here. N plus 1 into gamma n plus 1, we can replace it as gamma n plus 2. And here we have n plus 1 into gamma n plus 1 initially, that will be gamma n plus 2. Then we have n plus 2 here, and n plus 2 into gamma n plus 2 will be gamma n plus 3. Let me substitute this property. We get y1, that is capital Y1 equal to x by 2 whole power n 1 by gamma n plus 1 minus x by 2 whole power 2 1 by gamma n plus 2 plus x by 2 whole power 4 1 by 2 into gamma n plus 3. Now this can be written for standardizing or generalization purpose. Let me add few terms here without loss of any generality. That is, first term minus 1 power 0, which is 1 only, so there is no change in expression. Also 0 factorial, which is also 1, so there will not be any change. Gamma n plus 1 as it is. X by 2 power 0, so it is 1, so no change. And plus minus 1 power n 1, so minus 1 power 1 is 1. So in previous summation we had minus term, so we just replace it by minus 1 power 1 divided by 1 factorial, which is 1 only, gamma n plus 2 x by 2 whole power 2 plus minus 1 power 2, which is plus only, so no change. 2 factorial, 2 is written 2 factorial, gamma n plus 3 into x by 2 whole power 4 plus etc. This is just written for generalization purpose. So if you write like this, what will be the rth term? Here 0, when r equal to 0, minus 1 power 0. When r equal to 1, minus 1 power 1. When r equal to 2, minus 1 power 2. So in general term, when r equal to r, it will be minus 1 power r. Similarly, when r equal to 0, 0 factorial. When r equal to 1, it is 1 factorial. When r equal to 2, it is 2 factorial. So in rth term, in denominator, we have r factorial. Similarly, for 0th term, gamma of n plus 1, first place it is gamma of n plus 2. Third place we have gamma of n plus 3, means rth place we will have gamma of n plus r plus 1. Similarly, 0th place we have x by 2 power 0. First place we have x by 2 power 2. Second place we have x by 2 power 4, that is 2 into 2. So rth place we will be having x by 2 power 2r. So we write outside 1 x by 2 power n is there. Summation r from 0 to infinity, we write the general term minus 1 by 1 minus 1 power r by r factorial x by 2 power 2r into 1 by gamma of n plus r plus 1. Now taking x by 2 power n and clubbing with x by 2 power 2r, we get x by 2 power n plus 2r. This function is called the Bessel function of the first kind of order n, denoted by Jn of x. So we have Jn of x as summation r from 0 to infinity minus 1 power r by r factorial x by 2 power n plus 2r into 1 by gamma of n plus r plus 1. Similarly, when k equal to minus 1, we will get another solution, and this solution we denote it as j minus n of x. Thus, general solution is written y equal to a j n of x plus b j minus n of x, where a and b are arbitrary constants. So this is about Bessel's differential equation solution leading to Bessel function. So we derived Bessel function as Jn of x and j minus n of x. For watching.